Taking a look at some homework, worksheet number 16, curved mirrors. We got 3, 4, 6, and 7 we want to go over here. We'll get right at it. Number 3 says an object is placed 8 centimeters in front of a diverging mirror. Good idea, diverging mirror, to circle that and put F is a negative value. Whenever you see that word diverging, or in this case it would be convex mirror, okay, anything that means the same thing as diverging, then we should absolutely circle that in red or highlight it in pink or whatever it is that we do to draw attention to it. Has a radius of curvature of 8.0 centimeters. I'm going to circle that as well. Even though that's not one of those things that is typically what I'm going to circle in red, okay, it's not a negative value. It's not a south. It's not a funny direction thing or a unit conversion thing. I want to draw attention to it because the radius of curvature is related to the focal length. And the focal length is 1/2 of the radius of curvature. Therefore, the focal length will be 4 centimeters in this case. But with what we just circled a minute ago, diverging mirror, we're actually going to make it a negative 4 centimeters. So F is negative 4 centimeters, half the radius of curvature, or half the center of curvature. We want to find the magnification of the object. So we're going to say this is DO. This is where the object is placed. Okay, this is the focal length. We want to find the magnification. We got 2 equations, okay, and one of them is M is equal to HI over HO equals negative DI over DO. It's the one we're going to have to use, right? It's the only one with magnification in it. So let's try that. I don't know anything about H's, so that's out the window right now. DO, I know. DI, I don't. Going to have to find DI. There's only one other equation that I have. That's the magnification equation. Let's try that one to find DI. So let's say 1 over F is equal to 1 over DO plus 1 over DI. 1 over negative 4. And of course, if you make that a positive 4, everything's all wrong. Everything is off completely. A small difference in a sign here makes all the difference in the world for these questions. 1 over 8.0 plus 1 over DI. Now, we could rearrange this using common denominators there. The numbers are pretty simple, actually, to do common denominators, but I would suggest the easiest way is to do it with your calculator. Negative 4, x to the minus 1, subtract 8, x to the minus 1, because we take the 1 over 8 over by subtracting. Press enter, and then let's flip that over, x to the minus 1. We end up getting negative 2.66666. That's going to be in centimeters, of course. So now let's go back to the magnification and say negative DI. We just found that negative 2.6667 divided by DO is 8, right? Okay, and negative 2.67 divided by 8, I think, is a third, isn't it? 0.33. Going to be negative 0.33, right? What's wrong with that, Brad? Good. It's negative 2.67, right? We can't just drop the negative 2.67 or the negative in front of that just because we already have a negative there. The negative was there for a reason. The negative is here for a reason. We got to put them both in. We do the math there, it works out to be 0.33. Or you could put 0.33x afterwards, right? 0.33 times. Either's fine. Number 4, a store owner uses a, was there a question there? No. A store owner uses a diverging mirror with a radius of curvature of a meter. Diverging mirror again. Again, that makes F negative. And the radius of curvature, again, makes the focal length 0.50 meters. But we're going to make it negative because it's a diverging mirror. To keep an eye on the shoplifters, how tall would the image of a 1.8 meter tall man be? That's going to be HO, the height of the object. If you were standing 5 meters in front of the mirror, this is going to be DO. We're looking for HI. What do you want to start with? We're not looking for magnification, so there's nothing to tell us directly that we're going to start with the magnification equation. Actually, there is. There is. The only one with HI in there, which is what we're looking for, is the magnification equation. So I'm going to start with that one. But you know what? If you start with the other one, that's okay. This is just what I notice because I see I'm looking for HI. You start with the other one, that's fine. Okay, in the end, we're looking for HI. We've got HO. We've got DO. We need to find DI, and we're going to find DI using the other equation anyways. So again, whichever one you use first doesn't really matter. 1 over negative 0.50. And we're dealing with meters this time. Is that okay? Centimeters last time, meters this time? Sure, this is the one situation where it doesn't matter what units you use because the units cancel. We usually use centimeters because that's usually what we're given. Okay, but if we have meters given to us, that's fine. That's the standard units, in fact, as long as you're consistent throughout the problem. We're going to say 1 over DO is 1 over 5. Oops. It should be 1 over DI. Common denominator here would be 5, but personally, I think it's easier to do that little trick on the calculator. Negative 0.5 x to the minus 1. Let's subtract 5 x to the minus 1, because we've got to take that over by subtracting. Let's flip that over, and we get negative 0.4545. HI, HO is 1.8. DI is negative 0.4545, and DO was 5. So we take the 1.8 up by multiplying, and then we divide that number by 5, and we get what we get for HI. Who asked me for 3, and who asked me for 4? 4? Is that okay? Okay. Who asked me for 3? Is that good? And we had 7. Was there one more? 6 and 7? 6 says a 5 centimeter tall object produces an image that's 7 centimeters behind the mirror. The radius of curvature is 10 centimeters. We're going to say the focal length is 5 centimeters. Hey, this bothers me a little bit, though. 7 centimeters behind the mirror. What is that telling us exactly? That the image is behind the mirror. What kind of image does it have to be, Jack, if it's behind the mirror? Picture your ray diagrams in your head right now. Good. If you're looking into the mirror and you see an image on the other side, it's a virtual image. So we're going to make sure that we make that a virtual image. I'm going to make that DI, and I'm going to make it negative 7 to remind me that, again, DI is a negative value there. Radius of curvature is 5. Oh, wait, if we get a virtual image on the other side of the mirror, what kind of mirror does it have to be? Or do we know? Is this the one where I changed it? Yes, oh, good. Because I'm starting to worry here. As I'm reading this, I'm starting to worry. Like, wait a second, I don't think we can find the type of mirror in this. I think we had said that it was in a question in your version of it, it was converging. Okay, so it did say, all right, good. It did say that it was a converging mirror. Okay, the radius of curvature is 10 centimeters. That means the focal length is 5 centimeters, but it is positive 5 centimeters because a converging mirror produces a real focal point. Even though it's a virtual image, it's a real focal point. What's the magnification? All right, so let's say M is equal to HI over HO equals negative DI over DO. We don't know HI. Okay, we don't know DO. Okay, let's find DO. The only other thing that we can do is the mirror equation. 1 over F is equal to 1 over DO plus 1 over DI. 1 over 5 is equal to 1 over DO plus 1 over negative 7. Let's figure out what DO is. Let's say 5x to the minus 1, subtract, pay attention to this. We're subtracting what? Negative 7x to the minus 1, right? 1 over negative 7. Let's flip that over. We get 2.9167. And that's going to be in centimeters. So now let's find the magnification using negative DI over DO. Whoops, other way around, isn't it? Okay, whatever we get there, it's about 2.5-ish, 2 point something. Good? Good. All right, finally, let's take a look at number 7. It says, a 3 centimeter tall object produces a virtual image that's 2 centimeters tall. Okay, it's a virtual image. That doesn't mean this is negative, right? Okay, virtual image means that DI is negative. Now, we don't know what the value of DI is, I don't think. Oh, we do. Yeah. This is going to be DI. But let's make sure we make it a negative value. Virtual image has got to produce a negative DI. We get an HO, 3.0 centimeters. We've got an HI. Now, listen carefully here. We've got to think back to our A diagrams and imagine the situation here. Okay, it doesn't tell us whether this is right side up or upside down. We have to figure that out. When you have a virtual image produced in a mirror, is it going to be right side up or is it upside down? Think back to your ray diagrams. If you have to sketch a couple ray diagrams on scrap paper, that's okay. Every single time when you get a virtual image produced in a mirror, if it's a converging mirror, the virtual image will always be right side up. Yes. Okay. And if it's a diverging mirror, it's always going to be right side up as well. You said it's going to be right side up and bigger for a converging. It's going to be right side up and smaller for a diverging. The size doesn't really matter here actually right now. What matters is whether it's right side up or upside down. Okay. In a mirror, I mean, think about looking in the mirror in the bathroom in the morning. Are you right side up or upside down? When you get a virtual image produced in a mirror, it is right side up. That means HI will be positive. Okay, now, in the end, if we had forgot to pay attention to that, we would have gotten away with it. But what if it wasn't? What if a virtual image had always produced a negative or a flipped over image? Well, then we would have had to really pay attention to it and make sure we got it as a negative. Okay, we want to notice these things, even if in this case it didn't really affect us. Could have. HI is positive too because it's virtual. Positive not because it's virtual, but positive because virtual is always right side up. Distance from the mirror to the image, we want to find the focal length, and we want to find the type of mirror used. The focal length will tell us what kind of mirror is used, so we won't worry about that right now. Okay, I want to find the focal length. I'm going to start off with this equation because we know that we're going to end up using it at least. We want to find F. 1 over DO plus 1 over DI. I know what DI is. I got to find DO. So I'm going to go to my other equation. HI over HO equals negative DI over DO. I don't know what M is, but I know what HI is, and I know what HO is. It's going to be 2 over 3 equals negative 2.5. See that, guys? Negative. Okay, DI is a negative value because it's a virtual image. DO is what we're looking for. So DO goes up by multiplying, 3 goes up by multiplying, and then the 2 goes down by dividing. I get 7.5 over 2. 3.75 is DO. Is that right? And it's positive because of the negatives canceling there. All right, that leaves us with 1 over F is equal to 1 over 3.75, positive, plus 1 over DI, 1 over negative 2.5. This is one where we really want to use our calculator because common denominator here is a little bit trickier. So let's find it. Let's say 3.75 x to the minus 1, subtract 2.5, or you could add negative 2.5 x to the minus 1. It doesn't matter. It's the same thing. Let's flip that over, and we get negative 7.5 for F. What kind of mirror is that? What kind of mirror is that? And how do we know? Yep. It's a diverging mirror, and how do you know? Good, because the focal point is negative. You guys okay with that? We also had a little bit of homework due for today on page 665, all on the same type of stuff, but these are check and reflect questions, so the types of questions end up being a little bit different. We had a request to go over number 11, so let's do that right now. It says, some flashlights and headlights use concave mirrors or converging mirrors to help generate a light beam. If the light source is positioned at the focal point of the mirror, would all of the reflected rays travel outward parallel to the principal axis? Explain your answer, include a ray diagram. Well, let's go, Cassie, the other way around first. Let's say we've got a converging mirror. Okay, this is the focal point. This is the center of curvature or the radius of the mirror. Let's say that we've got an object out here where we have a whole bunch of rays reflecting. You know what? Forget about the object. Okay, the object is way, way, way far off. It doesn't matter where it is. We got a whole bunch of rays that are coming off of that object parallel to the principal axis because the object is so far away. Doesn't matter where they are exactly, except that they're parallel to the principal axis. Casty, where do they all go? Good. They all go through the focal point. So it's going to look something like this, right? This is your satellite dish receiver on the side of your TV, or sorry, on the side of your house. Usually you don't put it on the side of your TV. You usually put it on the side of your house or on the roof of your house. The rays coming from this distant satellite in the sky are all parallel to each other. They all hit the satellite dish receiver. They reflect and they converge at one spot. And that's where that big thing is, that detector is, detects a signal, and okay, you got more signal because it's a whole bunch of rays reflecting into one place. Well, you can imagine perhaps if you have an object right there at the focal point, not an object that's far off. Okay, that object that's at the focal point is going to produce rays of light in every which direction, including the directions you see here. If the ray of light will come this way, parallel to the principal axis, and then through the focal point, if it's coming the other way, from the focal point to the mirror, it's going to reflect back parallel to the principal axis. So all rays of light will reflect back parallel to the principal axis. Now, that doesn't mean a ray of light's not going to go down here and miss the mirror. That's not going to be reflected parallel to the focal point. But the rays that actually hit the mirror will be reflected parallel. So what's the purpose of that? You got a car with a headlight. Why do you want all the rays of light to go, or at least lots of the rays of light to go parallel to the principal axis? You want to have a beam of light that is directed in front of you, right? You don't care what's off in the field way over there. You care about most of your light being directed right in front of you on the road. So they direct the light right in front of you on the road by this converging mirror. All right? Does that make sense?